Hello everybody. I'm Sergis Bardaguer from Progetone project. Progetone is an European project which is developing new solutions to increase the energy efficiency and the seismic safety in the building sector. We are in the final year of the project, which started in 2017. And for this final year, we have several webinars which are intended to increase the knowledge and some awareness raising actions to understand the need of the project and why it can be really useful for the future of the construction sector. So today we will talk about seismic safety and which are the situation and potential solutions to increase this strengthening of the buildings regarding seismic issues. So we have with us three experts. Professor Ihsan Bal, he's a professor in earthquake resistant structures at Hanze University of Applied Science in the Netherlands. He's a civil engineer with expertise in seismic design, strengthening and monitoring structures. We have also with us Giuseppe Margani, which is professor of building construction at the University of Catania in Italy. His research focus on sustainable architecture, energy and seismic renovation, and innovation in building technologies, amongst others. He's coordinator also of the eSafe project, which is a sister project of Progetone, also addressing seismic strengthening solutions for the housing sector. And finally, we have also Stefan Ott. He has been working in construction research for more than 10 years at the Technical University of Munich in Germany. His research projects focus on improving the energy efficiency of existing buildings through prefabricated facade elements based on renewable raw materials. And he's an active partner of Progetone project. So for all of you that may not know this webinar, we will start with some presentation, 5 minutes per speaker, per expert, and then we will have a round table of around 15 minutes. If you want to ask some questions, you can put in the comments in the YouTube channel, and we will try to answer them or some of them depending on the number and the timing. So I would say the order, the agenda is we start with Ihsan Bal, then Giuseppe Margani, and finally Stefan Ott. So I will stop my sharing, and Professor Bal, if you want to share your screen.
Okay, you can see my screen, right?
Yeah, perfect.
Okay, thank you, Sergis. And today, well, I don't have much time anyhow, so I will try to be quick. Thank you to the Progetone team. So I will talk very shortly about feature of seismic strengthening, and I will give two examples very shortly. So what is the reason for seismic strengthening? Why we do seismic strengthening? I worked also as an engineer in companies for seismic strengthening. I did it as an engineer also. So many times people have different reasons, but the main idea from earthquake engineering perspective is saving lives. I have an example here, an earthquake that happened a bit more than a year ago in October 2020 in Samos, very close to Samos Island. It's a Greek island in the Aegean Sea. Magnitude 6.9. It caused, I think, only one death in Samos, but 72 kilometers away in Izmir, in Turkey, it caused 117 deaths. And 116 of 117 deaths occurred in 6 buildings. They were buildings that were constructed the same period between 1990 and 1998. They were all 7-8-story buildings, reinforced concrete, very close to each other in the same neighborhood. So all these 6 buildings created the total death toll. And the focus was not the Samos Island, but it was Izmir, although it was far away from the from the epicenter. And these 6 buildings are among 200,000 buildings. So it's really like a very, very, very small amount in the entire building stock. But they write the history because these 6 buildings are enough to create a catastrophe and cause 116 deaths. So at the end of the day, why Izmir was in focus instead of Samos? Well, it's very simple, because of the death toll. So the basics, if we go back to the basics of earthquake engineering, the main idea, if you isolate everything else, our idea is to save lives, period. But in order to save lives, we have to prevent collapse. So preventing collapse, if you look at the whole seismic safety issue from earthquake engineering perspective, and if we have a list of priorities, on top of the list by far is preventing collapse. So the idea is that in order to prevent collapse, we need to strengthen buildings. We cannot rebuild all the buildings. So it's a very similar problem to the energy efficiency. The problem is not the new construction. The problem is the existing building stock that is huge and it has many problems. So transforming this existing building stock is really the core of creating a seismic safe Europe. In order to do that, we are stuck in all the countries. We are stuck also in the US. It is the same problem. How to find the bad apples, the rotten apples. From 200,000 buildings, how to find these 6 buildings that will collapse. Of course, it's almost a mission impossible because it needs an incredible engineering effort. So maybe instead of doing that, we should twist the problem and just do no regret measures. No regret measures are the measures that need less engineering effort, but at the end of the day, you prevent the buildings from collapse. And at the same time, even if it is not perfect, it's a no regret measure because it is not perfect, but at the same time, it saves lives. I cannot get into more detail in 5 minutes, but just take a reinforced concrete building that is vulnerable to collapse. We know where they are. We know what type of buildings they are. We have all this knowledge. If you just close your eyes, don't do any analysis, and add 4 shear walls, 2 shear walls, reinforced concrete shear walls in one direction, and 2 shear walls in the perpendicular direction, it's very highly probable that you will prevent this building from collapsing. Of course, you need to do all the engineering work. I'm not saying not to do the engineering work, but if you do not have the means to do the engineering work for 200,000 buildings, only doing this no regret measures can save many lives. We did something similar here in Groningen. We did the experiment Kravert. If you are interested, I can provide you with more details later. But what we did is that we picked 40 houses. We sent structural engineers. They cooperated with the owner and the architects, and they didn't use any computer simulation. They only used their experience because they strengthened the same type of houses again and again and again. So they know what is needed. And it was much cheaper and faster, and people were happy because if people waited for the strengthening, they would wait at least 3-4 years due to the procedures. But we were able to do it very fast. So the discussion is that we need a twist in this earthquake resilience and earthquake resistance issue. We need to focus on collapse vulnerability. We should use no regret strengthening measures. We should be able to spot individual regions, buildings, or building groups and prioritize them against collapse. And we should also be able to use better tools in strengthening. We should be able to use emerging technologies. And of course, these all can be combined with the deep renovations. That was my fast-minute presentation. I will stop sharing my screen.
Thank you very much, Ihsan. Very interesting, this information. We need to know about that, yeah. So now, Professor Margani, you have sent us a video about the eSafe solutions. I'm sharing it now for all of you.
In earthquake European countries, renovation actions aim at improving both the seismic resistance and the energy efficiency of the existing building stock are strongly needed, looking at the resilience of buildings against earthquakes as one of the main values of a sustainable city. In this framework, the SAFE project is developing and demonstrating new technical solutions for the seismic and energy renovation of reinforced concrete frame buildings. The project has received funding from the European Union's Horizon 2020 Research and Innovation Programme. It started in October 2020 and will run for a total of 4 years. 12 partners from 8 European countries contribute to its implementation. The ECLT system is the seismic technology that drives the ESAFE retrofit innovation. It consists in the application of cross-laminated timber panels on the outer wall of the existing building by means of innovative energy dissipation devices. The aim of the system is twofold. For moderate ground motions, CLT panels allow the increase of the seismic capacity of the existing structure. Instead, for strong ground motions, the dampers dissipate part of the input seismic energy. These two features of the ECLT system allow the reduction of the storage of demand of the structure and consequently the reduction of its damage. The dissipative device is a friction damper. It consists of 2 steel profiles which connect the CLT panel of 2 consecutive floors with the existing interposed RC beam. One profile is connected to the RC beam by anchor bolts. The other profile is provided with slotted holes and is connected to the first one by pretensioned high-strength bolts. During an earthquake, when the force transmitted by the damper attains the value of the design friction force, the upper profile slides on the bottom one thanks to the slotted holes, thus dissipating seismic energy. The energy dissipation by friction ensures the durability of the structural efficiency of the damper even after seismic events, avoiding the need for its removal and replacement. The activation of the damper by a predefined force also enables to control the internal force on the CLT panels, which can be designed to avoid their damage and the need of their replacement after the seismic event. The ECLT panels are conceived to be prefabricated and thermally insulating and to be combined with the structural panels, which are applied to the windowy walls and are provided with high-performing windows in replacement of the existing ones. If the ECLT technology is not applicable or is not sufficient to achieve proper levels of seismic improvement, the EXO solution can be adopted. The system provides to connect to the existing RC structure an external steel exoskeleton equipped with seismic dampers. The result is a new external shell for the existing building that acts as a seismic resistance and energy efficient skin and allows to minimize the occupant's disturbance and to reduce cost and time for implementation. New technical systems are also combined to the ESAFE envelope solutions to reduce fossil fuels consumption and to maximize energy production from renewable energy sources. The systems include plug-and-play decentralized water tanks for domestic hot water storage, reversible electric heat pumps fed by on-site photovoltaic production, and insulated centralized tanks to decouple energy production and demand.
So, very interesting solution also from ESAFE project. Now, Stefan, can you share the screen?
Yes, I will start. So I hope you can see the screen now.
Yeah, perfect.
Okay, yeah.
Yes.
So hello also from my side. I will show you some alternative solution for systems for seismic strengthening of buildings, and mainly for the background from the in front of the background of the climate neutrality pathway and the environmental impact of such building on construction measures. So what we are facing this is that we have to reduce our emissions not only in operations of buildings but also in the construction of buildings, in the use of materials, because otherwise we will not achieve these zero emission pathway until 2050, and we have to think about what solutions are the most valuable and contributing the most to the climate neutrality pathway. And there are two strategies. One is to, as Ishan Bal already said, is to renovate our building stock to avoid to destroy a lot of values and materials which are out there already. And the other thing is that we have to choose the good solutions and the most efficient structural components and materials to do this. So what we are talking about in Progettone is these kind of strengthening systems which we started with. So that's existing structure on the left-hand side. We add the steel exoskeleton to this structure, and then there are also add-ons like balconies or extra spaces or sun spaces to these structures. The structure is mainly for the improvement of the seismic safety of the building. And then these other components are increasing the energy efficiency of the building and also give additional space to the building or additional value. So the increasing the floor space for the inhabitants and making the building still more valuable. But when we talk about these solutions made from steel or aluminum, they are partly very good in structural terms, but on the material side and on the environmental impact side, they are less optimal. So we thought about some different solutions, and I will show you now these post-tensioned cross-laminated timber structures. First of all, this is a two-dimensional variation of these post-tensioned structures, and it consists of a frame which is put in front of an existing wall of a building, and then there is this red infill from insulation material, and you see also these post-tension rods which are connecting the columns with the beams, and then you can add in the final stage some additional insulation and cladding according to your requirements for energy efficiency that you need. And these structures could also be three-dimensional, so that you really have also the value of additional space of these structures. They are not only two-dimensional frameworks, they are here really spatial structures. So they are consisting out of CLT elements or panels in orthogonal to the existing structure. And then there's also these other components added, like the infill for the windows or for the parapet for balconies, or it's an insulation layer and the additional cladding of the facade. And we had several hypotheses to examine these CLT exoskeletons, and we claim them that they are low carbon components, and additional have the seismic strengthening exoskeleton function. So I will not focus on the seismic strengthening function, but more on the low carbon issue. There are some other articles out there about the seismic strengthening capability, so you can find them on the Progettone homepage and can have a look at this. And then we will also show that there is a substitution potential compared to steel or aluminum exoskeleton variants for these post-tension timber CLT structures. And then these renovating existing structures lead also to an overall reduction of global warming potential. Instead, if we tearing down the buildings and build them entirely from the ground up. So we did this life cycle analysis, mainly with the focus on the on the material indicators for the production of the material, for the end of life of the materials. We excluded the construction stage and also the use stage because the data is less available there. And then we found out that we can achieve deviation about 90% for the 2D exoskeleton and up to 75% for the 3D exoskeleton made out of timber post-tensioning structures. Yeah, and that's it for the overview. And now I'm open for some questions.
Thank you very much, Stefan. So now I would have, we are starting the roundtable. I would have several questions, and if any of the viewers have any question, they can you can put in the comments. So the first one, these are open questions, so all of you can answer. The first one will be, what are the differences between low and high seismicity zones in Europe in terms of practical implications of seismic strengthening and renovation? So who wants to answer this question?
Well, I can step in, but maybe also Giuseppe can say things because it's also part of ESAFE, the moderate and high seismic regions. Well, I think the main thing is the seismic demand, of course. If the seismic demand is really, really high, well, we have pre-code buildings. Pre-code buildings have no or very low level of seismic loads considered during the design. So if you go to no-code or pre-code buildings, basically you don't have much difference within Europe because they are all designed under the dead load, the self-rate. So in that case, if you are in a very high seismic region or in a very low seismic region, basically you get more or less the same section dimensions. It's not much different. But after the 70s and 80s, the seismic codes and the seismic hazard started to become more and more prominent. And then the drifting away in different countries in Europe starts. So the seismic countries start to get more stronger buildings in this period. But if you go back to 70s, buildings are almost all the same. In that sense, if you want to do strengthening in low seismic areas, you need less intervention. It is easier. It is more feasible. In the high seismic areas, you need much stiff elements. You need extra stiffness. Extra stiffness, you cannot get extra stiffness with just strengthening. You need to add elements. Either you need to add new elements, like an exoskeleton, or you need to make the existing elements bigger, fatter. So that also needs some foundation strengthening. So the amount of effort is not linear. If you go from moderate or low seismicity to high seismicity, in the high seismicity, you need much, much more effort. New foundations, that's already a big problem in the strengthening business. New foundations, big elements, new elements, that has other implications. But in the low or moderate seismicity, maybe you can save the structure with much less intervention, then it becomes more feasible.
Okay, thanks. Giuseppe, do you want to add something?
No, actually, I mean, in regards to this question, I would say that yes, there are some solutions like the exoskeleton ones for very strong earthquake. We need for sure very stiff elements, as Ishan said. But it's a really challenging such a kind of intervention. In ESA, we try to focus more on earthquake, which are not the strongest one, because we know that for these situations, I mean, we did a lot of money and a lot of efforts. But I would like also to underline that many European countries have not so a high level of seismicity, and so we can also find solutions that are not so heavy and not so in terms of again, money expenditure and so on. This is what I want to add. But I mean, what Ishan said, it's my opinion. I agree totally with his position.
Okay, regarding this point, I have another question. Are there any architectural features that can limit the application of these solutions that you have explained from Progettone or eSafe project or other similar solutions? Are, for example, the type of buildings, type of, I don't know.
If you want, I can give an answer from my side, of course, from eSafe, or Stefan for Progettone, as you wish. Okay, I can start.
Both of you, yeah.
As regards eSafe, we show actually two solutions, the eXOS and the eCLT. eXOS, we have to develop more in detail in the next year. We have more information about the eCLT. And in my opinion, also eCLT has more limitation than eXOS. And it's also a more, I would say, a more innovative and also less disruptive for the residents. So I would like to focus on the eCLT from the structural and the CLT panels, structural panels. So actually, for eCLT, we need regular openings on the facades, which must be vertically aligned. And this allows us to uniformly apply the panels to each building story. Moreover, I would say that less than 60% of the facade should be provided with windows to apply the structural panels to an adequate facade extension, I would say. And another limitation is that if you have at the ground floor many garage with big doors, or if you have many shops with big and large windows openings, it's also actually a problem, because you don't have at the ground floor enough facade, enough surface to put on the eCLT panels. This would be also a limitation, a problem. And then another lower limitation are the bow windows, so projecting windows from the facades. In this case, you are not allowed to connect the CLT panels with their dampers directly on the reinforced concrete beams. And finally, the last limitation at this stage we can see about the effective use of eCLT regards the number of floors. We are quite sure that up to 6 floors, this solution is quite effective. Above this number of floor, above 6 floor, we have to check this out, but I guess that it will be much less effective. Despite this limitation, we are really confident that it is still a very promising technology. Tomorrow we are going to test in Bologna one-to-one reinforced concrete frame equipped with seismic dampers, the steel dampers that we show in the video, and with the CLT, of course, with all of the sensors, and we will make this real test to better understand the efficiency of the system.
Right.
So we will see.
Great. And Stefan,
just one short addition. I also see some problems in buildings which have very high modulation in the facade, like balconies. They are a huge effort to cut them back. Otherwise, they are interfering with the structure, with the two-dimensional, as Giuseppe said, or also with the three-dimensional exoskeletons. And we see this in our demo case in Athens right now, and that's also a problem, so to say.
Okay. Yeah.
Maybe also the problem is that in Progettone you are going to add additional volumes, additional spaces. We thought about this problem also with Anarita Ferrante from Progettone when we were writing the eSafe proposal, and that's the reason why we made another solution, the eAxos, which are actually bidimensional exoskeletons, or also three-dimensional ones, but they don't need to add extra volumes to the external of the buildings. And so maybe we can, for example, spare the balconies. We can leave the balconies on the buildings in this sense. Of course, it's two different concepts. Your idea is really effective, it's really good, but as you know, we need the permission to have an additional volume outside the building.
Okay. So I would also, we have no question from the viewers, so we have another question here that which will be, or what's the benefit of using timber? That's mainly for Stefan, of using timber and other renewable materials regarding climate neutrality pathway.
Yeah. So yeah, as you have seen in the comparison of the different types of exoskeleton structures, there is a huge benefit for timber, because if you think of the biogenic carbon cycle, when you grow the wood in the forest, then it extracts the carbon dioxide from the atmosphere. It's, so to say, a natural carbon sink. And then you harvest it, then you spare or store the carbon in the building for a long time, and you do not release it to the atmosphere again. So it's more beneficial instead of burning biogenic fuels. Yeah, that's not so good idea. But with this storage, we save the biogenic evaporation of these greenhouse gases and let them in the building stock for a long time. And that's the very important benefit we see there. And additionally, there's another benefit that if we do not tear down the existing structures, we had in the project some calculations from our partners from Lima as well, and from Bologna, that we can save about up to 55% of the emissions when we keep the existing structure and add some stiffening or seismic strengthening measures instead of tearing them down.
Okay. Thank you very much. It would be great to continue talking about this interesting subject, but I think that we need to close now this webinar. As you may know, this webinar is it's developed in the framework of a webinar cycle from Progettone project. So more webinars will come during next month until the end of the project, with several subjects and topics. So thank you very much, Giuseppe, Ihsan, and Stefan, for this interesting discussion. And
you're welcome.
And keep in touch.
Welcome. Yeah. Thank you.
All.
Thank you very much.
Thank you. Bye-bye.
Bye-bye.